Hi everybody, welcome to Physics 1, lecture number 6. Today we're going to focus on forces. In particular, we're going to focus on Newton's third law of motion. For every action, there's an equal and opposite reaction. We actually covered quite a bit of stuff in our last lecture. I skipped over the review from the previous lecture on vectors because you've got that video. You can go back and re-watch that and reread the slides. We talked about force and superposition, Newton's first and second laws of motion, inertia and force and acceleration, free body diagrams, gravitational force, all that covered in our last lecture. So today we're going to look at Newton's third law. For every action, there is an equal and opposite reaction. So the first thing we're going to talk about today is a normal force. What is a normal force? So if I'm standing on the ground, there is a force acting on me. There's actually two forces. There's one force going down, that's the force of gravity. Gravity's pulling me down. That's my weight, mg. But the ground is holding me up. I'm not falling through. I haven't gone down to the second floor and the third floor in the basement. I'm still standing here. So the floor is pushing against me. It's equal but opposite. That is the normal force. So if you're standing on the surface, the push back on you from the surface is the normal force. Normal, of course, means perpendicular. So we can rewrite it like this. We just got a very simple diagram. We have a table with the block on it. The weight of the block is the force of gravity, mg, pulling down. The normal force, which is force N, is pushing back. It's exactly the same, just the opposite direction. So let's look at an example. The normal force for a block resting on a horizontal surface that is accelerating vertically at AY. So this is actually something that is accelerating upwards, like a lift. So say we're standing on a lift, or in a lift, and we're going up to a higher floor, we're going to pop up to floor number 7. It starts to accelerate upward. In that case, the normal force is my weight plus that mass times acceleration going upward. Well, my mass hasn't changed, so that factor can be taken out, we factored out, and then it's simply mass times the sum of those two forces. But if I'm at rest vertically, if I'm in the lift and the lift is stopped, it's just mg. It's just my weight. That's the normal force. It hasn't changed. So checkpoint number 3. The magnitude of the normal force greater than, less than, or equal to mg if the block and table are in an elevator going upward at constant speed and an increasing speed. So it says 5.7, must be referring to this one here. All right, so here's our image. So it says, is the magnitude of the normal force greater than, less than, or equal to mg if the block and the table are in an elevator or a lift moving upward at a constant speed, or B, at an increasing speed? Well, if it's at a constant speed, or if it's going in this direction at a constant speed, that's a constant velocity. If it's constant velocity, the acceleration is 0. If the acceleration is 0, then the force is 0. Therefore, there's no acceleration. It's simply equal to mg. That's the normal force. But if we're in a lift and it's an increasing speed, that means there is an acceleration. That means it's going to be greater than mg. If it's going up, you feel that when you're in a lift and you go up, kind of feel your weight increase a little bit. So it's going to be greater than mg. It's going to be mg plus that acceleration that you're going up in the lift times your mass. So that magnitude of the normal force is going to be greater than mg in that case because it's accelerating. If it's not accelerating, if it's constant speed, or if it's 0, the magnitude of that normal force is going to still be mg. So what about friction? Okay, we've spent several lectures talking about things where there's no friction, this little ideal world that doesn't exist. In reality, we have friction. Friction is a force. How do we account for that? How do we conceptualize it? So, frictional force occurs when one object slides or attempts to slide over another. So anytime you have two things connecting, two objects on the surface, and you move it across, all the little fine all the little imperfections in that are going to cause friction. So if I'm trying to push it in this direction, the frictional force is going to be working against it. It's kind of like a normal force. It's not really normal force because the normal force is up here. But it works in opposite to the attempted direction of our sliding in this case. So we push it this way, the frictional force is working that direction. Tension force. So we have a cord or a rope or a chain or something like that. It's attached to a body and pulled taut. So if I'm pulling something, there's a force, a tension. The cord pulls in the body with the force T directed along the cord. So if I'm pulling an object in this direction, the force isn't going to be up, it's going to be pulling in that same direction. The cord is said to be under tension, and we simply use the capital T to describe that. A massless and unstretchable cord exists only as a connection between two bodies. So, again, we're simplifying things a little bit. We assume a massless cord because we're trying to think of things a bit more simply. It's not stretching, an ideal situation. But we're going to be utilizing this for some of these problems. It pulls on both with the same force T. So if I'm pulling on a block, the same force on either end of that is the same. So this is true even if the bodies in the cord are accelerating and even if the cord runs around a massless, frictionless pulley. So there are going to be lots of questions where you've got a block, here's a pulley, the cord goes up and around, and I'm trying to pull it. The reason we use those bloody pulley examples is because it gives you practice on trying to calculate these forces when there's an angle involved. It's not straight up or down, not straight side to side, there's some angle. So they're just simplifying assumptions. So here you can see you've got a block and you've got somebody pulling it. The tension is along the rope with the cord being pulled. And that's just assuming there's no mass of the cord and the cord doesn't stretch. Remember, when we're looking at forces, if we're pulling with our hand, the origin of the force is our hand, the tension is going in towards the block, or if the block is pulling, it's resisting and the tension is going in this direction. We would not write it as the origin of the vector here, and the tail's going, or the head's going in the other direction. Or we can pull it around a pulley. So in this case, the tension is going upwards. In this case, it's going horizontal. It's just three different examples. They all work in the same basic principle. So checkpoint number 4. The suspended body in figure 5.9c weighs 75 newtons. Is the tension equal to, greater than, or less than 75 newtons when the body is moving upward at a constant speed, an increasing speed, or a decreasing speed? Well, the mass of this. If we're pulling down at a constant speed, it's not going to change. There's no acceleration. It's going to be equal to 75 newtons. If we're pulling up at an increasing speed, then the tension is going to be greater. It's like pulling something really hard, you're going to jerk it. You're going to almost snap it because you're increasing the amount of force there. So if we increase the speed, it's accelerating opposite to gravity, that tension is going to increase. So it'll be greater than 75 newtons. If it's at a decreasing speed, it's going to be less than 75 newtons. So decreasing speed means we're just sort of letting it up on it. We're decreasing the tension by letting up on it. This guy again comes up a lot. For every action, there's an equal and opposite reaction. Objects interact when they push or pull on each other. So a more formal way of saying Newton's third law, when two bodies interact, the forces on the bodies from each other are always in equal magnitude and in opposite direction. So we're going to write it down mathematically. We can write this as a scalar or a vector relation. So as a scalar, the magnitude is the same. So it doesn't matter about direction. The magnitude is the same. In this case, as a vector, we remember that the opposite direction is the other force. So the force of B on C is one direction, the force of C on B is always opposite. So they're equal in magnitude, but opposite in direction. So we can call these two forces the third law force pair. Anytime any two objects interact, there is a third law of force pair. So you're always going to have that with an interaction of two objects. So using the Earth as an example, so in this case we have the force of the cantaloupe on the table and the force of the table on the cantaloupe. I don't know why the hell they use weird fruits like this, but okay, we've got the cantaloupe pushing down the table pushing back up. So equal forces in magnitude but opposite in direction. And same if you look at it with the cantaloupe Earth interaction. Yes, so here you have the cantaloupe pulling down, being pulled down by the Earth, and the surface of the Earth is going to push back. It doesn't matter what surface it is. So reciprocal gravitational forces between the Earth and the cantaloupe. This is pretty straightforward. It's pretty obvious. What about action-reaction forces? A sample problem, a block of mass 3.3 kilograms connected by a cord and pulley to a hanging block of mass 2.1 kilogram slides across a frictionless surface. Well, let's start to put in all of our forces, our free body diagram. I'll define something free. So we've got our mass here. So we've got the force of gravity pulling down, we've got the normal force pulling up, and we've got the force of the other block going in this direction. So right now, I believe they've just taken the force of friction out, or else there would be a force going in that direction of friction. But right now, it's just no friction. On this block, there's only two forces acting. There's the force pulling down from gravity, and the tension of the force pulling up. This tension and this tension, the same magnitude. So now we're going to draw a free body diagram. We draw all the different forces involved. We're going to treat the string again. It doesn't stretch. The pulley's massless and frictionless. Each block is considered a particle. Just simplifying this. Draw the free body diagram. Remember, we've got our normal force going up. We've got our force of gravity going down. We've got the tension going the positive x direction for the first one. In this case, the acceleration is this way, because the table's not moving, it's not lifting off the table, it's not falling through the table. So the acceleration in this is sort of canceled out between these two, but it is moving in this direction, so it's being pulled across by the weight of the other block. In this case, the acceleration is going downward because of gravity. The tension of that and the force of gravity are both canceling out. Or they're equaling each other out. But the overall thing is moving because there's no friction on this first block here. Because there's no friction here, it's sliding off in this direction. The whole thing is moving like this. It's going down. So we apply Newton's second law with the different forces in each of the masses. In this case, the mass is larger and this mass is smaller. It's 3.3 kilograms and 2.1 kilograms. So we eliminate all the unknowns, the tensions that are the same, and solve for the acceleration. So we're actually going to solve this problem here. For the sliding block, the tension is equal to the large mass times acceleration. Because in this case, the acceleration is going to be the same for both of them. For the hanging block, the tension minus the force of gravity is equal to minus small ma. So this minus this is going to be equal to the overall mass acceleration. We can combine those two factors. So we simply plug this to here and then solve for acceleration. We get equation 521. We can just keep moving around to get the tension in both those cases. So plugging in, we find the acceleration is 3.8 meters per second squared, and the tension is 13 newtons. So once we find our acceleration, we simply take that number, we plug it back in here, and that gives us our tension. So check that the dimensions are correct, check that A is less than G, check that the tension is less than mg, otherwise the acceleration would be upward. So this is just simply a matter of checking your solution. Now, if you remember the last lecture, I said I was going to put up a video. That video is not part of the normal lectures. It's not lecture 5, 6, 7, or 8. It's an independent video where I explain to you how to go about solving one of these word problems. So here's a good example of that. Simple problem is that it gives you the details, so you read the whole problem and you're trying to figure out what it's asking. So you read the problem, what are they asking about? They're asking you to calculate the acceleration and the tension. You draw your diagram, you label all the forces in your diagram, you write down all the information that it gives you, the different relative masses, you know G, for example. You draw your free body diagram, you write down the equations that you know you're going to be using in this case, and then from that, you can begin to solve things algebraically first. Once you solve them algebraically, then plug in the numbers. But don't start plugging in the numbers before you solve it algebraically. That just opens up so many possibilities and chances for mistakes, and they're very common when that happens. Once you're done, you have your answer, you make sure your units are correct, and then you check your answer. Does it make sense? So this just follows the algorithm that I showed you in that video on how to solve problems in physics, how to solve word problems in physics. So here's a fun sample problem. This is a block being pulled up a ramp. So here's a situation where we've got to utilize all these forces in not such a straightforward way. It's not simply X or Y. We've got an angle theta here. So in this case, the box accelerates. It's held on to a cord. All right, let's draw our free body diagram. We've got the force of gravity pulling down. We've got the normal force up. And it's not just straight up and down. It's actually directly perpendicular to the box and the ground, the surface here. So that normal force is in that direction. The direction it's being pulled is in the X direction. We have the force of gravity here. So again, we have to break up its constituent points utilizing the Pythagorean theorem. So we've got to look at our different trig components here to figure out what these different forces are doing. So we've got mg here, we've got mg cosine theta there, and mg sine theta in that component. So we just have to work out those different components here. So given a graph of an object's acceleration, a versus time, its acceleration versus time, we can integrate to find the velocity. This is just going back to our basic principles of calculus again. This is something that I did last week in 3 dimensions, or the last lecture in 3 dimensions, and a couple lectures ago in 1 dimension. We're just doing our basic derivation of projectile motion, but in this case it does actually projectile motion. It doesn't make any difference really. So we have our initial time and our final time. We integrate over that. We can evaluate it from the graph. This just shows, of course, the area between the acceleration curve and the time axis from the initial time to the final time. This just goes back to basic calculus, which you've already learned and we've already applied a couple of times. Taking a graphical approach, we can integrate the velocity. So given a graph of an object's velocity versus time, we can integrate that to find its position. Again, we did that a couple of lectures ago. I think it's really important that all of you take the time to practice that derivation of projectile motion, those equations we use, because that's going to come up. You are going to need to know that. So you need to be able to do that derivation. So we're going to define, we have a definite integral, which means it has boundary values. Just leaving this for a second, 12 years ago when I was teaching physics at the University of New South Wales, we had students coming into first year calculus-based physics, same subject you're taking now. In their labs, they were doing some integrals, and when they were doing that, they were saying, oh, well, the integral is something plus c. Plus c, that's an indefinite integral. If it has boundaries, then it's a definite integral. And in physics, in these cases, you're going to be using boundaries. So your initial time, your final time, initial position, final position, initial velocity, final velocity, they are going to be bound. So the definite integral on the right can be evaluated from the graph. We've done this before, same thing. It's the area between the velocity curve from time initial time to our final time. So a particle of mass m moves in one dimension. It's subjected to a force F. The force can be written in terms of time, or it can be written in terms of position with respect to time, where that x of t defines the motion of the particle. So we're going to sample the motion at regular times. So for each time interval, it's going to be t of I, for I being equal to 0, 1, 2, whatever. Such that that interval time plus 1 minus the interval time is equal to delta t. We're going to set our initial time at 0. I hope it's confusing enough for you. If that change in time is sufficiently small, we can simply write it in these terms. Our position with our I plus 1 minus our position I over delta t is our velocity with respect to I, and we can expand that to our acceleration. So we can express the velocity and the acceleration directly in terms of the sample values of the position, x of I, at the time samples t of I, provided that delta t is small enough. So this is an algebraic approach to it, of course. So force is equal to mass times acceleration. We substitute a of I, that equation we had before. We plug that in, and then we can solve for x. So we know that our initial position and our initial velocity, if we know that, we can determine our x1. We know our initial position in x1 and our force 1, we can determine x2, and so on. x1, x2, force 2 can determine x3. And then we plot this algebraic solution in purple using 15 different points. For F is equal to negative kx. Negative kx, that's a spring force. Yes, there are certainly more complicated practices. They're generally based on Euler's algebraic method. So in summary, we talk about Newtonian mechanics. We got forces of pushes and pulls that cause acceleration. Forces are vector quantities measured in newtons, the sum of all forces on a body. This is a summary of our previous lecture. We talked about weight. This time we've talked about tension. We've talked about friction along a surface. We've talked about normal forces. A lot of it's been, pretty much the entire lecture has been about Newton's third law, action equals reaction. It's a law of force pairs. If there's a force by B on C, then there's a force by C on B. It's just meaning the magnitudes of these forces are the same, but the directions are opposite. So we've looked at graphical and algebraic representations of motion. I've done a pretty shit job at explaining those, so I'm going to splice in some videos that are a bit better at putting those across. So next lecture is going to focus on 6.1 through 6.3 chapters.